Hello students, welcome all of you. In this video, we will discuss an important topic in thermodynamics, Carnot cycle on TS diagram, that is temperature entropy diagram, and the expression for the efficiency of a Carnot engine from a TS diagram. We know that PV diagram, that is pressure volume diagram of a Carnot cycle, consists of two isothermal processes represented by the curve AB and CD respectively. AB represents isothermal expansion, while CD represents isothermal compression, and also two adiabatic processes. PV diagram of Carnot cycle consists of two adiabatic processes represented by the curves BC and DA respectively. Curve BC represents adiabatic expansion, while curve DA represents adiabatic compression. Thus, PV diagram, that is pressure volume diagram of Carnot cycle, is a complete reversible cycle. In PV diagram of Carnot cycle, pressure is represented along y-axis, while volume is represented along x-axis. Hence, it forms a rectangle, that is PV diagram of Carnot cycle forms a rectangle on TS diagram, that is temperature entropy diagram. TS diagram of Carnot cycle is represented in figure 2, in which temperature is taken along y-axis, while entropy is taken along. Entropy is denoted by the symbol capital S, temperature is denoted by the symbol capital T. So, entropy S is taken along positive x-axis, while temperature represented by the symbol capital T is taken along positive y direction. So, TS diagram of Carnot cycle is a rectangle consisting of two isothermal processes represented by the sides AB and CD of the rectangle formed ABCD, while two adiabatic processes represented by the two remaining sides BC and DA of the rectangle formed. Suppose during the isothermal expansion, which is represented by the side AB of the rectangle, it occurs at constant temperature, say temperature is T1, but entropy of the system means ideal gas kept inside the cylinder of a Carnot engine, but entropy of the system increases from S1 to S2 during the isothermal expansion, which is represented by the side AB of the rectangle formed ABCD, but it occurs at constant temperature T1. आइसोथर्मल एक्सपेंशन टीएस डायग्राम में, कार्नोट साइकिल का टीएस डायग्राम में कांस्टेंट टेम्परेचर T1 पर अकर होता है, लेकिन इस आइसोथर्मल एक्सपेंशन में इंट्रोपी, सिस्टम का इंट्रोपी, सिस्टम मीन्स आइडियल गैस kept inside the cylinder of a Carnot engine. The entropy of the system, that is ideal gas, increases from S1 to S2 at constant temperature T1. So isothermal process is represented by the side AB of the rectangle on temperature entropy diagram. During adiabatic expansion, which is represented by the side BC of the rectangle, temperature of the system changes or falls from temperature T1 to T2, but entropy of the system remains constant, that is entropy in this case is S2. We have taken in the TS diagram. Entropy is constant. At constant entropy S2, temperature of the system changes from T1 to T2, represented by the side BC. During isothermal compression, temperature of the system remains constant. Isothermal compression के केस में temperature of the सिस्टम का टेम्परेचर, आइडियल गैस का टेम्परेचर, जिसे सिलेंडर में कार्नोट साइकिल के कार्नोट इंजन के सिलेंडर में रखा जाता है, तो आइसोथर्मल कंप्रेशन जिसे रेक्टेंगल ABCD के साइड CD से रिप्रेजेंट किया गया है इस TS डायग्राम में, TS डायग्राम ऑफ कार्नोट साइकिल में, तो आइसोथर्मल कंप्रेशन में टेम्परेचर तो कांस्टेंट रहता है, which is temperature is T2, but entropy of the system falls from the value S2 to S1. So during isothermal compression, of Carnot cycle on TS diagram, temperature of the system remains constant, that is T2, while entropy of the system falls from the value S2 to S1. Now in adiabatic compression, which is represented by the side DA or AD of the rectangle, this is adiabatic compression. So during this adiabatic compression, represented by side DA of the rectangle, entropy of the system remains constant, that is which is S1. Entropy of the system is S1, which is constant, but temperature of the system increases from T2 to T1. That is during adiabatic compression, the system returns back to its initial temperature and also pressure. So this is four processes involved in the temperature entropy diagram of a Carnot cycle. Now we have to obtain the expression for the efficiency of a Carnot engine using this TS diagram. For this, suppose Q1 be the heat absorbed by the system from the heat source during the process of isothermal expansion, and Q2 be the amount of heat rejected to the sink by the system, that is by the ideal gas, during the isothermal compression. Isothermal compression is represented by side CD of the rectangle, while isothermal expansion of Carnot cycle on TS diagram is represented by the side AB of the rectangle. टीएस डायग्राम में साइड ए बी के द्वारा आइसोथर्मल एक्सपेंशन को रिप्रेजेंट किया गया है कार्नोट साइकिल का, जबकि साइड सी डी रेक्टेंगल का साइड सी डी द्वारा कार्नोट साइकिल का आइसोथर्मल कंप्रेशन को रिप्रेजेंट किया गया है। तो सपोज किया जाता है कि Q1 अमाउंट ऑफ हीट है जिसे वर्किंग सब्सटेंस और सिस्टम विच इज एन आइडियल गैस केप्ट इनसाइड द सिलेंडर ऑफ ए कार्नोट इंजन। तो सिस्टम आइसोथर्मल एक्सपेंशन के केस में जिसे ए बी से रिप्रेजेंट किया गया है, तो Q1 हीट सोर्स से सिस्टम एब्जॉर्ब करता है इस आइसोथर्मल एक्सपेंशन प्रोसेस में, जबकि आइसोथर्मल कंप्रेशन प्रोसेस में Q2 अमाउंट ऑफ हीट रिजेक्ट करता है सिस्टम सिंक को। सिंक इज ए कोल्डर बॉडी at temperature T2 Kelvin, while heat source is a hotter body at temperature T1 Kelvin. So Q1 amount of heat Q1 which is absorbed by the system during the isothermal expansion AB represented by AB of Carnot cycle. So Q1 will be equal to T1 multiplied by AB, that is change in entropy, using the relation change in entropy ds is equal to amount of heat absorbed or rejected, that is dq upon absolute temperature, that is mathematical form of second law of thermodynamics, which is ds is equal to, we know ds is equal to change in entropy is equal to amount of heat absorbed or rejected by the system to the, that is ratio of amount of heat added or absorbed or rejected by the system to the absolute temperature. So using this relation we can obtain dq, that is amount of heat absorbed by the system or rejected by the system. We can calculate dq is equal to T multiplied by ds. So using this relation we can write amount of heat absorbed by the system during the isothermal expansion from the heat source is Q1 is equal to temperature is T1. During the isothermal expansion, temperature is constant, which is T1, and change in T1 multiplied by AB, that is change in entropy. AB represents change in entropy also. Corresponding to point A, entropy of the system is S1, and corresponding to point B, entropy of the system is S2. So it is T1 multiplied by AB, that is S2 minus S1, S2 minus S1. Q1 is equal to T1, and T1 is represented by AH. In T1 is the higher temperature, that is temperature of the heat source. So T1 is represented by side by the side AH of the rectangle ABGH. So it is AB multiplied by H multiplied by AB. So T1 corresponding to T1 we can write AH multiplied by S2 minus S1, that is change in entropy. Change in entropy is represented by AB. So AH into AB, AH multiplied by AB is the area of rectangle. We can write it as the area of rectangle ABGH. It is area of the rectangle बराबर area of the rectangle ABGH. It is the amount of heat absorbed by the taken by the system during the isothermal expansion at constant temperature T1. So it represents Q1 is equal to T1 multiplied by change in entropy S2 minus S1. T1 is corresponding to T1. We have written AH, side AH of the rectangle, and corresponding to S2 minus S1 represents AB. So it is area of the rectangle ABGH. Now Q2 is the, suppose Q2 is the heat rejected to the system during this isothermal compression, which is represented by side CD of the rectangle. So Q2 is the amount of heat rejected to the sink and it can be written as using the relation dq is equal to T multiplied by ds. So Q2 is equal to temperature is here temperature is T2, that is temperature of the sink, multiplied by CD. CD is represented by S2 minus S1. There is decrease in entropy, so it is S2 minus S1. And corresponding to T2, we can write HD or DH is equal to T2. Corresponding to T2, we have DH multiplied by S2 minus S1. In this case, is represented by DC. So DH multiplied by DC is the area of the rectangle DCGH, that is area of the rectangle. We know the formula of rectangle, length into breadth. So DH multiplied by DC is the area of the rectangle, DCGH. Suppose it is equation number 2. Now difference in difference in Q1 and Q2, that is difference of Q1 and Q2, amount of heat taken from the system, by the system from the heat source Q1, and Q2 is the heat rejected to the sink during the isothermal compression, represented by side CD of the rectangle. So difference in Q1 and Q2, that is the difference Q1 minus Q2, and it is equal to work done by the system, and which also represents the energy available per cycle, heat energy available per cycle. It is equal to Q1 minus Q2 will be equal to work done, and this will equal to the available energy, heat energy per cycle also. So Q1 minus Q2 is equal to area of rectangle ABGH minus area of the rectangle DCGH. So area of the rectangle on TS diagram ABGH minus area DCGH. तो एरिया हमें क्या मिलेगा? द रिजल्टेंट एरिया इज ABCD. तो हमें एरिया ऑब्टेन होगा ABGH एरिया में से, रेक्टेंगल का एरिया में से DCGH रेक्टेंगल का एरिया DCGH को माइनस कर लिया जाए. रेक्टेंगल ABGH का एरिया AB मल्टीप्लाइड बाई एरिया ऑफ रेक्टेंगल ABGH में से एरिया ऑफ रेक्टेंगल DCGH को माइनस कर लिया जाए, तो रिजल्टेंट एरिया क्या होगा, क्या बचेगा? ABCD, दैट इज एरिया ABCD. This is ABCD, and ABCD represents it will be equal to Q1 minus Q2. It will be equal to Q1 minus Q2, and ABCD is equal to AD multiplied by area of ABCD means AB into BC, and BC represents or AD represents T1 minus T2, while AB represents either S2 minus S1, and in this process, isothermal process, Q1 is the heat taken by the system from the heat source. So this will equal to work done. Q1 minus Q2 is equal to work done. So W is equal to work done by the ideal gas in one complete cycle. W is equal to Q1 minus Q2, and it is equal to area ABCD, that is AB multiplied by BC, that is area ABCD बराबर है area of the rectangle we know, length into breadth, so it is AB multiplied by BC. It is AB multiplied by BC. BC is T1 minus T2. Now we have calculated net work done by the system, by the working substance during one complete cycle on Ts temperature entropy diagram. Now we have to obtain the expression for efficiency, expression for the efficiency of uh, the Carnot engine. So we know the formula for efficiency is eta equals to, that is, the formula for efficiency of a heat engine is W upon Q1, that is net work done by the system, ratio of net work done by the system to the heat taken by the system from the heat source. So the efficiency, write down the efficiency of a Carnot engine is given by eta equals to W, that is Q1 minus Q2, work done by the system upon heat absorbed by the system from the heat source, and W is Q1 minus Q2, upon Q1, and it is equal to Q1 minus Q2 represents, Q1 minus Q2 is equal to work done, and this represents the area of the rectangle ABCD. So we can write in place of Q1 and Q2, Q1 minus Q2, we can write Q1 in place of Q1 minus Q2, we can write, we have already used it, area of rectangle ABCD. So area of rectangle ABCD divided by Q1. Q1 is the heat taken. Q1 is the heat taken from the heat taken by the system working substance from the heat source. So in place of Q1 minus Q2, we have taken area of rectangle ABCD, and in place of Q2 we can write we have used Q2 is equal to T2 multiplied by S2 minus S1 using the relation dq is equal to T multiplied by ds. So in place of Q1 we can write area of, in place of Q1 we can write we have already used Q1 is equal to amount of heat taken by the working substance or system from the heat source. Using the relation, we have already used it, we have already calculated it. Q1 is equal to T1 multiplied by S2 minus S1, and it represents the area of the rectangle, that is T1 corresponding to the side AH of the rectangle, while S2 minus S1 represents GH. So Q1 corresponds to the area of the rectangle ABGH. So it is area of the rectangle ABGH. So in the denominator we can write in place of Q1 area of the rectangle ABGH. We have already used it. We have already calculated Q1 and Q2 using the relation ds is equal to, change in entropy ds is equal to dq upon t, that is dq is equal to T multiplied by ds in equations 1 and 2. So area of rectangle ABCD is AB multiplied by BC. So we can write AB multiplied by BC upon area of rectangle ABGH corresponding to Q1 is AB multiplied by AH. So it is AB multiplied by AH. AB multiplied by AH. AB and AB will cancel out in the numerator and denominator. So we have the expression for efficiency of a Carnot engine is eta equals to BC upon H, and BC is T2 minus T1. BC is T2 minus BC is T1 minus T2. So BC is T1 minus T2 and AH is T1. AH is T1. Corresponding to H, temperature of the system is T1. So it is T1. So efficiency of a Carnot engine is finally given by T1 minus T2 upon T1. That is T1 by T1. We can also write, suppose it is equation number 4, and we can also write it as eta equals to T1 by T1 minus T2 by T1, that is 1 minus T2 upon T1. And this is the final expression for the efficiency of a Carnot engine, which is eta is equal to 1 minus T2 upon T1, or we can also write it as from this relation eta equals to 1 minus Q2 upon Q1, and final expression is eta is equal to 1 minus T2 by T1, where T1 is the temperature of the heat source while T2 is the temperature of the sink. Now the importance of TS diagram, that is practical utility of TS diagram, is TS diagram is very helpful for the study of heat engines. We can easily calculate the area, that is area on TS diagram represents the total work done by the system in one complete cycle, and which is also equal to the available heat energy per cycle. So TS diagram has practical utility for the study of or working of heat engines, or for the study of heat engine. And since the simplicity of the figure, we can easily compute the area of the cycle, and area of the cycle we know represents area of the cycle represents the heat energy available per cycle, and area ABCD represents the total work done by the system during the complete cycle, which is represented by the difference of heat Q1 and Q2, that is heat taken from the heat taken from the heat source Q1 during isothermal expansion AB, and Q2 is the heat rejected by the system during the isothermal compression. Now this video is completed. Thanks all of you for watching my YouTube channel Physics Quantum Classes.